Now let's talk about the different ways of representing a graph. A graph can be represented in two basic ways. The first one is adjacency matrix and the second one is adjacency list. So adjacency matrix, it says that it's a matrix, right? And matrix basically means it's a two-dimensional array. A two-dimensional array will surely contain rows and it will also contain columns. So the horizontal lines, say for example, this is a horizontal line, this one is a horizontal line. So the horizontal lines are called the rows and the vertical lines are called the columns. All right. And the intersecting box, this is an intersecting box, this is an intersecting box. So the intersecting box between the row and the column, between the row and the column, will show whether a pair of vertices has some kind of edge between them. So if there's an edge, we write 1 in it. If there is no edge present, then we write 0 in it. So let's see this with the same example. You can see the graph here, and it's an undirected graph that contains 5 vertices A, B, C, D, and E. So we have to first create a matrix. The matrix will be equal to n into n. So n basically represents the number of vertices. Since there are 5 vertices, so the matrix will be of size 5 into 5. There will be 5 rows and there will be 5 columns, and each row is named after the particular vertex. Say for example, this row is named after A vertex, this row is named after B, this is C, this is D, this is E. Similarly, this column is named after A vertex, this is after B, this is after C, this is after D, and this one after E. So since it's a matrix and it's a two-dimensional array, whenever an array is declared, it's initialized with values 0. So by default, these boxes will contain 0 in it. So now let's check whether each of the pair of vertices have some kind of edge between them. If there is an edge, we will replace the 0 with 1. So let's see, is there any edge between A and A? Is there any self loop? No, so 0 remains 0. Is there any edge between AB, A, B? Yes, there's an edge between AB. So let's replace it with 1. Is there any edge between A, C? Again, I'm telling the row number first and then the column number. Is there any edge between A, C? No, there is no edge between AC, so this remains 0. Is there any edge between AD? The row number is said first and then the column number. AD, there is an edge, so I write 1. Is there any edge between AE? No, it remains 0. Similarly, I check whether there's an edge between BA. The row number is said first and then the column BA. There is any edge? Yes, there's an edge between BA, so I write 1 here. Is there any edge between BB? There is no self loop, so I write 0. BC, yes, there's an edge, so I write 1. BD, yes. Then BE, yes, there's an edge, so BE is also 1. Again, CA, is there any edge? No. CB, yes. CC, no. CD, no. CE, there's an edge. Similarly, the row number again said first. DA, is there any edge? DA, yes. DB, yes. DC, no. DD, no. And DE, yes, there's an edge. Again, EA, there is no edge. EB, there's an edge. EC, there's another edge. ED, there's one edge. And EE, there's no edge. So my adjacency matrix is populated and it's complete. Now, since this is an undirected graph, you can find a sequence out here. You can see that this particular row is 0 1 0 1 0. Again, the first row becomes equal to the first column, 0 1 0 1 0. There is a proper symmetry in it since it's an undirected graph. It's very simple logic. You can see that A and B has an edge between them. That means there's an edge from A to B and there's also an edge from B to A. So AB is 1 and also BA is 1. Similarly, AD has an edge. That means there's an edge from A to D. That means the this particular the first row, the row number is set first and then the column is set next. So there's an edge from A to D, so AD contains 1 in it, and again there's an edge from D to A. Since it's an undirected graph, we can uh, tell it in both ways. That means there's an edge from D to A as well. So DA is also 1. As a result, you can see that first row is equal to the first column. Second row 1 0 1 1 1 is equal to the second column 1 0 1 1 1. Third row 0 1 0 0 1 is equal to the third column. Fourth row is equal to the fourth column. Fifth row is equal to the fifth column. Since it's an undirected graph, there is proper symmetry in it. Now let's talk about the adjacency matrix for a directed graph. For a directed graph, there cannot be any proper symmetry in it, because if I tell that there's an edge from A to D, I cannot tell that there's an edge from D to A, right? The direction is given here. So there's an edge from A to D. So AD will contain 1 in it, but DA will contain 0 in it. So let's see this with this particular adjacency matrix. First and foremost, we need to create the matrix, and in order to create the matrix, we need to decide the size of the matrix. Again, there are 5 vertices. As a result, this will be a 5 into 5 matrix, A B C D E, A B C D E. Now let's see, is there an edge from A to A? No, there is no self loop, so 0. Is there any edge from A to B? From A to B, yes, there's an edge. Is there any edge from A to C? A to C, no edge. A to D, there's an edge. Yes, you can see there's an edge. A to E, let's see, A to E, no edge, so 0. Again, let's check for B. Is there any edge from B to A? No, there is not any edge between from A to B, from B to A, sorry. So it's 0. Similarly, is there any edge from B to B? No. Is there any edge from B to C? From B to C, yes, there's an edge, so 1. From B to D, is there any edge? No, there is no edge. There is an edge from D to B, but not from B to D, so B to D remains 0. Then B to E, B to E, there's an edge, so it's 1. Similarly, you can do this for the other leftover vertices as well. You can see for C, there is no outgoing edges, right? From C, I'm going nowhere. Am I going to A from C? No. Then am I going from C to B? No. Am I going or is there any self loop between C? No. Am I going from C to D? No. Am I going from C to E? No. So this particular row completely becomes 0. You can try out for D and E as well. It's pretty simple. Now let's talk about another effective and efficient way of representing a graph, and this time around I'm talking about the adjacency list. So adjacency list, most of the things about an adjacency list for an undirected graph and directed graph are very common, but there is a slight difference. Let's start with the adjacency list for an undirected graph. So you can see an undirected graph here, and this is the adjacency list for this undirected graph. So the first thing that you need to do is create a billing like structure like this one. So this building like structure will actually contain blocks. Blocks of what? Blocks of vertex. So blocks of all the vertices that are present in this particular graph. So if this graph contains 5 vertices, then there will be 5 blocks: A, B, C, D, E. If there are 100 vertices, then there will be 100 blocks, and each block will be named after the vertex. So this block is for vertex A, this block is for vertex B, this is for C, this is for D, and this one is for E. If there are 10 million vertices, then there will be 10 million blocks. So you need to create this particular building of blocks first. This is common for both directed and undirected graph. So after creating these blocks, what you need to do is list all the vertices that are adjacent to each block or each vertex. So this is a block of vertex A, right? So you need to list all the vertices that are adjacent to A. So you can see that B is adjacent to A and D is adjacent to A. So you write B first in another block and D next in the last block. Since there are no more vertices that are adjacent to A, so we stop here and give this particular sign. This sign is very important, so look at it very closely. And you have to give this arrow sign as well. Next, we need to list all the vertices that are adjacent to B. So you can see that A is adjacent to B, D is adjacent to B, then E is adjacent to B, and C is adjacent to B. So how do we write it? We write it in alphabetical order. We write A first, then C, then D, and then E. So A, C, D, and E. Next, you can see that C has B as an adjacent vertex and E as an adjacent vertex. So we write B and E. Next, for D, you can see that A is adjacent, B is adjacent, and E is adjacent. We write it in alphabetical order: A, B, and E. Lastly, there are no more vertices left which are adjacent to D. As a result, we give this particular sign. Then E, for E you can see that D is adjacent, B is adjacent, and C is adjacent. So we write BCD. So we write BCD. So we are done creating the adjacency list for an undirected graph. We just list all the vertices that are adjacent or that are adjacent or that are incident to each vertex or each block. This basically means that we are listing out the edges, right? All the edges. Say for example, A has an edge with B, A has an edge with D, so we are writing BD. Now let's look at how to create an adjacency list for a directed graph. You can see a directed graph here, and the common thing is you need to create this building of blocks first. Each block will be named after the vertex that is present in the graph. This one is named after A, this is named after B, this one after C, this one after D, and this is named after E. So we have created the block or the building like structure that we needed to create for the undirected graph as well. Now what we need to do is list all the edges that are outgoing from each block. In the undirected graph, what we did was we listed all the edges that are adjacent to each block or each vertex, but this time around we have to just list all the edges which are outgoing from each block. So you can see that for vertex A there are outgoing edges to B, and there is an outgoing edge to D as well, so we list B and then D. Then for B we can see that there's an outgoing edge to C, and then there's an outgoing edge to E, so we list C and then E. Then for C you can see that there are no outgoing edges, so we keep it empty and give this particular sign. Remember this sign, this is very important. And for D you can see that there's an outgoing edge to B and there's an outgoing edge to E, so we list B first and then E. And lastly for E there's an outgoing edge only to C, so we list C. We are done creating the adjacency list. So since we are creating an adjacency list that lists out all the edges that are outgoing from each vertex, we can also create an adjacency list that will list all the edges that are incoming to a certain vertex or a certain block. So let's see this. You can see that for block A there are no incoming edges. You can see that for block A there are no incoming edges. You can see that for block B there are no incoming edges. You can see that for block C there are no incoming edges. You can see that for block D there are no incoming edges. You can see that for block E there are no incoming edges. You can see that for block F there are no incoming edges. You can see that for block G there are no incoming edges. You can see that for block H there are no incoming edges. You can see that for block I there are no incoming edges. You can see that for block I there are no incoming edges. You can see that for block J there are no incoming edges. You can see that for block K there are no incoming edges. You can see that for block L there are no incoming edges. You can see that for block M there are no incoming edges. You can see that for block N there are no incoming edges. You can see that for block O there are no incoming edges. You can see that for block P there are no incoming edges. You can see that for block Q there are no incoming edges. You can see that for block R there are no incoming edges. You can see that for block S there are no incoming edges. You can see that for block T there are no incoming edges. there are no incoming edges. There are only two outgoing edges to B and D. So we do not list anything out here. Then for B, you can see that there are two incoming edges from A and then from D. So we write A and D. For C, you can see that there are two incoming edges, B and E, so we list B and E. For D, there is only one incoming edge from A, so we list A. And lastly, for E, you can see that there is an incoming edge from D and incoming edge from B, so we go in the alphabetical order and write B first and then D. So we have created the adjacency list for all the edges that are outgoing from each vertex, and we have created another adjacency list for all the edges that are incoming to each vertex or each block. I hope this video makes it clear the difference between the adjacency list for a directed graph and the adjacency list for an undirected graph.